Hello, and welcome back to the Cosmic Companion. This week we're joined by Dr. Allison Youngblood of the University of Colorado Boulder. She recently used the Hubble Space Telescope to look at the atmosphere of Earth during a lunar eclipse, testing methods we may use to find life on other worlds. In addition, we talk with Professor Jane Charlton of Penn State University about last week's virtual Astrofest. Also on this episode of Astronomy News with the Cosmic Companion, we take a look at the dwarf planet in the inner solar system, Ceres, as new evidence comes to light revealing a vast ocean beneath its frozen surface. We'll learn about a possible answer to the great mystery of why the star Betelgeuse recently dimmed for several months, and talk about the Perseid meteor shower, and spotting shooting stars in the late summer skies. The dwarf planet Ceres is the largest member of the asteroid belt, which orbits between Mars and Jupiter. New findings from the now-defunct Dawn spacecraft reveal large oceans of salty water under the frozen surface of our neighborhood dwarf planet. Although it contains 1/4 of all the mass found in the asteroid belt, Ceres is just a small fraction of the size of the best known of all the dwarf planets, Pluto. Still, one ocean under the frozen surface of Ceres was found to be several times deeper than even the deepest ocean trench on Earth, the Challenger Deep. The dimming of Betelgeuse, seen at the end of 2019 and the beginning of 2020, was likely the result of dust blocking light, data from the Hubble Space Telescope reveals. Hot plasma likely rose up from beneath the surface of the star before charging through the super-hot atmosphere surrounding the red giant. As the cloud expanded and raced away from the star, the exiled material, including ionized magnesium, cooled and grew darker, blocking light from reaching Earth. Dr. Andrea Dupree, who led this study, will appear on next week's episode of Astronomy News with the Cosmic Companion, coming Tuesday, August 25th. Make sure to tune in. As events of all types move online, the astronomy conventions of the near future are likely to be held in virtual worlds as well. These events hold great promise, and creating them is a challenge facing researchers hoping to bring their knowledge to the public in the era of virtual classrooms. We talk with Professor Jane Charlton from Penn State University, founder of Astrofest, about bringing this year's event online.
Since we already had a video game, and even actually a company associated with game development that started at Penn State, we were able to pretty easily come up with a lobby for hosting Astrofest. We let our volunteers put together a bunch of videos of various lengths, talking about things that they're passionate about. And we put a bunch of our mini games from our course into the Astrofest environment and a virtual observatory.
How do you hope to use virtual environments like this in the future for teaching astronomy and astrophysics?
Well, we were actually talking about that last night. During the event, we were on all these different Zoom webinars with each other, And we were talking about, hey, maybe we could use a lobby much like this for a virtual field trip for elementary school students, where we replaced some of the more advanced, longer talks with videos of demonstrations for kids and some things that would be more appropriate for that age group. And so we were talking about maybe putting a program like that together for the coming school year, given that kids are not going to be likely to be able to take regular field trips right at this time.
Right.
We also plan to leave this Astrofest area online, replacing our live components with resource lists of some of our favorite things for teaching astronomy online. And that way it will be available for people to explore for free around the world for a long time to come.
So next year, assuming it's possible to do an in-person Astrofest, do you still want to have some sort of virtual component to future Astrofest?
I don't think we would do it at the same time virtually, because we only have about 100 people around our department, and we'd be pretty busy with the in-person thing. But I think at different times, swapping things into the lobby, and then we could promote the virtual Astrofest after the fact, maybe with new presentations and things every year. So maybe it has started something.
The Perseid meteor shower took place last week, peaking on the nights of August 11th and 12th. Despite light from the moon drowning out views of some of the dimmer shooting stars, the event showed several dozen meteors per hour to viewers over most of the world. There are several minor displays of shooting stars happening over the rest of August. Sky gazers under dark, moonless skies looking to the east after midnight should spot a shooting star once every 4 or 5 minutes. This week, we are joined by Dr. Allison Youngblood, an astronomer from the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder. She recently led a study using the Hubble Space Telescope to examine ozone on Earth, testing methods which could be used to one day find life on other worlds. This week on Astronomy News with the Cosmic Companion, we're happy to be joined by Dr. Allison Youngblood. She is an astronomer with the University of Colorado Boulder. Welcome to the show, Allison.
Thank you. Thanks for having me.
Thank you. So you recently participated in a project that some people are calling the ultimate Earth selfie.
Yes.
Tell us about what you did.
So I led this Hubble Space Telescope proposal and observation to observe a lunar eclipse with the Hubble Space Telescope. So the Hubble Space Telescope is in low Earth orbit, and during a lunar eclipse, if you were an observer with the telescope on the moon's surface looking back at the Earth in the sun, you would see the Earth transit the face of the sun, much like how an exoplanet transits its parent star. And that's one of the main methods, transits are one of the main methods that astronomers have for probing exoplanet atmospheres. So this was like probing Earth as a transiting exoplanet. And we were basically taking a selfie because the moon was reflecting the sunlight. And we were, the goal of the experiment was to measure ourselves, to measure what is in Earth's atmosphere.
And so why would you use, the Hubble is normally used for deep space observations and, measuring things, observing things, far, far away. Why would you use Hubble to look at something as close as the Earth?
Right. I think that this may be the closest thing that Hubble has ever observed, and that made this really challenging. I can go into more details later. So the reason that we used Hubble is because Hubble, first of all, is an astronomer's telescope. It's the kind of telescope that we will have, like it's set up the same way, as opposed to some telescopes that may be more dedicated, say, to solar physics or studying nearby planets. This is an astronomer's tool, and we were trying to test an astronomer's tool on the Earth, which is the only habitable and inhabited planet that we know about. So we thought it would be a good idea to characterize what the Earth looks like exhaustively at all different wavelengths. And so what the unique thing that Hubble provided was access to ultraviolet wavelengths, which has to be done from a space telescope. So this experiment with a lunar eclipse of, Earth taking a selfie has been done many times before, mostly from the ground, actually exclusively from the ground, I think. And this was the first time a satellite looked at a lunar eclipse for that purpose.
Super. What advantages are there to looking at this in ultraviolet light?
In the ultraviolet, there are a lot of really strong atomic and molecular transitions. For spectroscopy, which is a tool that astronomers have for gauging what things are made of in the universe, the ultraviolet is like a key place for seeing really strong signatures of things, meaning that you don't need a whole lot of a substance, a certain type of atom or a certain type of molecule to translate into a large detectable signal. And specifically for studying Earth's atmosphere, we have an ozone layer, and the ozone spectral signature in the ultraviolet is extremely strong, very, very strong. And that's, what helps us not get at least as bad sunburns as we would if there were no ozone layer. The Earth protects us there. And so that's what we were measuring. You can measure ozone, at optical wavelengths or at infrared wavelengths. I believe that James Webb will have the ability to measure ozone, maybe not on an exoplanet, but it has access to the right wavelengths. But the ozone wavelength, the ozone spectral lines in the ultraviolet are so bright and strong. And so what that means, one cool aspect of that is, especially if we, in the future, if astronomers use an ultraviolet telescope to study distant, potentially Earth-like planets, and they're looking for ozone, the ultraviolet would allow you to detect ozone, even if there wasn't a whole lot of it there. Like even just a few billion years ago, Earth didn't have nearly as much oxygen as it has today. And so if you were maybe, say, trying to detect ozone with like a James Webb-like instrument, you would only have access to these weaker ozone spectral signatures, and you may not be able to detect ozone from like a young Earth analog. But in the ultraviolet, you could.
And why is ozone important? Why are we looking for it?
Ozone is potentially a biosignature. So here on the Earth, ozone is a byproduct of molecular oxygen, which is an output from photosynthesis. So it's literally a signature of life. That's why we have oxygen in our atmosphere. And with the next generation of telescopes coming up, we're going to be trying to identify whether or not there's life or at least habitable conditions on other planets. And ozone is one of the features that we'll be looking for.
And so ozone then is primarily a product or a byproduct of life on this planet. And so
yes,
that's
on this planet.
Right.
Yes.
And so just through the laws of chemistry, that's what we're expecting.
Right. Sunlight. Yes. Sunlight interacts with the molecular oxygen, O2, in our atmosphere to produce O3 or ozone. And, also ozone provides, with a protective layer so that surface life can, not be burned to a crisp or harmed irreparably. So there's also that added benefit. But there's also possible, ozone by itself is not a biosignature. There are other ways to build up detectable amounts of oxygen and then hence ozone via its, since it's a chemical byproduct of oxygen, that don't require life. So just if you go out and you look for ozone on an exoplanet and you find it, that does not mean that there's life there. You need other signatures as well, things like methane, for example.
Right. So at some point, with additional instruments and surveys, we'll probably find some exoplanets where we say, okay, we're seeing ozone, we're seeing it's in the Goldilocks zone, we're seeing some methane, but that's not as certain of a sign of life as, say, pi being sent down by, radio telescopes.
Right. Yes. And there's certainly a difference between intelligent life and just, maybe some form of microbial life on the surface or, plants. Yeah.
Right. So how do we go about telling planets where these sort of gases may have accumulated chemically as opposed to those where it came about through biotic or prebiotic processes?
So it requires not only measuring what is in that planet's atmosphere and taking a tally of what molecules are present and how much are they, but then some modeling to go on. And what I think that we'll be looking for is a sign that these biosignatures like O3 or methane are what's called out of equilibrium, that you can't just explain their presence solely through the starlight coming in at the top of the atmosphere and then whatever chemical pathways you're simulating from what you know is probably on the planet. And so without missing what is causing it to be out of equilibrium then would presumably be something like life. So it'll be an observation plus a modeling approach, looking for these kind of pairs of biosignatures.
What got you interested in looking at this?
So, exoplanets and studying things like it, I kind of stumbled on it in grad school, just trying to find an advisor, a PhD advisor to work with. But I connected with it really strongly. And I think for the same reason, I think a lot of people who are not even scientists can connect with it. Like it's just a human thing, a curiosity thing. Finding planets out there, characterizing them or helping to characterize them. There's so many things that go into that effort. It's just really exciting and feels meaningful.
All right. And so, I've talked to a few people who have worked with Hubble before, and I always ask this question. I'm going to ask it of you. What was it like to be able to work on this remarkable telescope?
Working with Hubble is such a treat. It's not like ground-based telescopes because they do not let astronomers like me control it. It's a major, delicate, but powerful asset. And so they have a whole team of astronomers in Baltimore, specialists who control it. So, all the prep work that I did for setting up the observations happened many months in advance. But you get notified when your observation is happening. And I don't know, it's cool to think like, wow, Hubble's out there doing something because I wanted it to.
Uh-huh. Wow.
Yeah, it's a real privilege. It's fun.
Was this your first chance to work with Hubble?
No, I worked on a lot of Hubble data as a grad student, and I've had several other programs where I was the principal investigator as well. So not my first, but I think it may have been the most exciting because just Hubble pointing at the moon is very rare and very special.
Yeah. And so what other future missions, we talked a little bit about Webb, but what other missions Webb included do you think can help us find signs of life on exoplanets?
Yes. So right now, the astronomy community is participating in this ongoing thing called the decadal survey, where every 10 years, astronomers get together and as a community decide what our priorities should be for the next decade. And that helps inform, it's a document that's commissioned by Congress, and it helps inform what types of studies that the NSF and NASA will give to scientists like me to do our research. And so right now, as part of the decadal survey, there are several big flagship type NASA missions that are being under consideration that NASA should go forward with. These things are incredibly ambitious and probably wouldn't be launched until the year 2035 or later. But there are two concepts in particular, well, three, that are for looking for biosignatures. And there's one called LUVOIR, which is being studied like in its biggest form. It would be a 15-meter telescope. It would be like Hubble, more with a structure of, like, it would resemble James Webb, but it would be more of a UV optical infrared telescope. So that's LUVOIR. And then there's something called HabEx, which stands for the Habitable Explorer, I think. And it would be a smaller telescope, but it would be dedicated exclusively to exoplanets, whereas LUVOIR would be truly more like Hubble, which Hubble does everything. And then there's something called the Origins Space Telescope, which is a far infrared mission. And it would have a more focused approach. It would be doing many things, but for exoplanets, it would have a very focused approach on exoplanets around red dwarf stars.
That's fascinating. And so are you going to be doing more research on ozone and in exoplanets, or are you going to be working with something else? Or what are your future plans?
So this was a project that was a little atypical for me. Most of my work is about characterizing exoplanet host stars. So and especially in the ultraviolet is where my expertise is. And so typically I'm not observing planets themselves, but their host stars. Because like I mentioned, when describing the chemistry that happens in planet atmospheres, the most important energy source for that is the ultraviolet spectrum. At least for the chemistry that happens in the upper atmosphere, which is the part of the atmosphere we probe with transit observations of exoplanets. So I take measurements usually with the Hubble Space Telescope to quantify, like say, Proxima Centauri, what does its UV spectrum look like exhaustively, and so that modelers can use it as an accurate energy input into their modelers of what they think, say, Proxima B's atmosphere looks like.
So you're mainly looking at stars that are naturally hotter, or are you looking for UV emissions from, say, coronal effects?
Yes, coronal effects. So I mainly look at exoplanet host stars. So stars that have exoplanets or that are good proxies for stars with exoplanets. And lately that's been these red dwarf stars, which are these very cool stars that the exoplanet community has been intensely focused on because these stars are so abundant. They tend to have a lot of planets, and these planets are very detectable compared to, say, Earth-like planets around sun-like stars. Those are hard with the technologies that we have today to not only detect, but also to characterize. And M dwarfs are very cool, or red dwarfs, same thing. The surface of the star is very cold, but they have this intense chromospheric and coronal emission that emits ultraviolet light. So yes, I study stars that are very magnetically active, and that's the source of their ultraviolet emission rather than just being big hot stars.
That's fascinating. Well, thank you so much for being on the show. It was wonderful to have you here.
Thank you. It was great.
And now it's Dr. Allison Youngblood, the astronomer at the University of Colorado Boulder. Next week on Astronomy News with the Cosmic Companion, we'll be joined by Dr. Andrea Dupree, a senior astrophysicist at the Harvard-Smithsonian Center for Astrophysics. We will talk about her work uncovering the mystery of why the red giant star Betelgeuse recently became dim for several months before becoming bright once more, an event witnessed by millions of amateur sky gazers here on Earth. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of The Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.